Learning objectives. In this chapter, the user will learn the following in detail: fundamentals, purpose, application, image processing system, components, image sensing and acquisition, sampling and quantization, neighbors of a pixel adjacency connectivity, regions and boundaries, distance measures, stereo vision. Introduction to image processing and computer vision. Image. An image is a two-dimensional function that measures of some characteristics such as brightness or color of a viewed scene. An image can be defined as a two-dimensional function x, y, where x and y are spatial coordinates and amplitude f at any pair of coordinates x, y is called intensity or gray level of the image at that point. An image is a projection of 3D scene into a 2D projection plane. Analog image. It is characterized by physical magnitude varying continuously in space. When x and y and amplitude values of f are continuous quantities, the images are analog. It cannot be broken into small individual pieces. Represented as continuous range of values representing position and intensity. Digital image. When x, y and amplitude values of f are all finite, discrete quantities, the image is digital. It is composed by picture elements which are called pixels. Pixels are the simplest form of an image. Pixels are used to represent brightness of an image. Conversion of analog image into digital image. Conversion of analog into digital images involves two important operations. These are sampling and quantization. Advantages of digital images. The processing of an image is fast and cost-effective. It can be easily stored and efficiently transmitted from one place to another. Copying of digital image is easy. The image would not be degraded even if copied several times. Reproduction of digital image is faster and cheaper. Drawbacks of a digital image. Anyone can misuse images by abusing copyright of images. Digital images cannot be enlarged. Memory is required to store good quality of images. Digital image processing. Processing of digital images by computers. Image is composed of finite number of elements. The image of the object is captured in imaging system in the form of transparency or photograph. The digitizer is used to convert original image to digital image by using sampling and quantization. It is then stored in computer memory. The images are displayed through television monitor. A mini computer may be used to communicate and control digitizer, storage, etc. The program inputs to the computer are made through a terminal and outputs are also available on a terminal. Computer vision. This is a branch of artificial intelligence and image processing concerned with computer processing of images from real world. Computer vision typically requires a combination of low-level image processing to enhance the image quality, and high-level pattern recognition and image understanding to recognize features present in the image. Advantages of processing images by computers. Flexibility and adaptability. When compared to analog electronics and optical information processing, no hardware modifications are necessary in order to reprogram digital computers to solve different tasks. Digital computers are ideal devices for processing image signals adaptively. Data storage and transmission. Development of image compression data can be effectively stored. digital data can be easily transmitted from one place to another. Digital image representation. Two-dimensional discrete signals. It has n star n elements. Each element in the array is a number which represents a sampled intensity. Converting image into digital image can be done by using digital camera and scanner. Digital images can be created directly on a computer screen. It is restricted in spatial coordinates sampling and allowed in intensities, quantization. Three types of image processing. Low-level image processing, mid-level image processing, high-level image processing. Please view the diagram. Low-level image processing. It is characterized by the fact that both its output and inputs are images. Example: noise removal, used to remove noise from an original image. Contrast enhancement, used to improve quality of an image. Image sharpening, highlights the edge of an image. Mid-level image processing. It is characterized by the fact that its inputs are generally images, but its output are attributes extracted from images, such as segmentation. Example: image classification. Assign a label to an object. Image segmentation, used to partition an image. High-level image processing. It is characterized by the fact that its inputs are attributes extracted from images and outputs are generally images. It involves object recognition and image analysis. Example: scene understanding, autonomous navigation. Please view the diagram. Origins of digital image processing. One of the first applications in digital image processing was in the newspaper industry when pictures were first sent by submarine cables between London and New York. Pictures were coded for cable transfer and reconstructed at the receiver end on a telegraph printer. Introduction to Bart Lane cable picture transmission system in 1920 reduced the time required to transport a picture across the Atlantic from more than a week to less than 3 hours. Specialized printing equipment was used to code pictures for transmitting via cable and then reconstruct the image from the code at the receiving end. In 1964, computers were developed to improve quality of images of Moon taken by the Ranger 7 probe. In 1970, digital image processing began to be used in the medical field. In 1979, Godfrey and Cormack shared the Nobel Prize for inventing medicine for tomography behind computerized axial tomography scans. Since 1980, digital signal processing is used in many fields like industrial, medical, military applications, etc. Digital image processing application areas. Improvement of pictorial information for human interpretation. Processing of image data for storage, transmission and representation for autonomous machine perception. Advantages of DIP. It improves visual quality of an image. It can easily process degraded images of uncoverable objects. It can process an image in such a way that the result is more suitable than the original image. Image compression technique can be used to reduce the amount of data which is required to represent a digital image. Mathematical and logical operations are performed on an image like addition or multiplication, etc. Image segmentation can be used to detect discontinuity, the presence and absence of specific anomalies like missing components or broken connection path. Limitations of DIP. It requires much storage and power for processing. Effective environmental conditions may degrade image quality. Segmentation of non-trivial image is one of the most difficult tasks in digital image processing. Applications of digital image processing: gamma ray imaging, X-ray imaging, imaging in ultraviolet band, imaging in the visible and infrared bands, imaging in the microwave band, imaging in radio band. Gamma ray imaging. Images based on gamma rays include applications in nuclear medicine and astronomical observations. In nuclear medicine, a patient is injected with a radioactive isotope that emits gamma rays as it decays. Images are produced from this emission and are collected by gamma ray detectors. Positron emission tomography. This is another modality for nuclear imaging. When a positron meets an electron, both annihilated and gamma rays are given off. These are deducted and tomography images are created using principles of tomography. X-ray imaging. Oldest sources of EM radiation used for imaging. X-ray used in medical field and other industrial areas like astronomy. In digital radiography, digital images can be obtained by following two methods: by digitizing X-ray films, by having X-rays that pass through a patient and fall onto a device such as a phosphor screen that converts X-ray into light. Imaging in ultraviolet band. It includes lithography, industrial inspections, microscopy and lasers, biological imaging, and astronomical observations. It is used in fluorescence microscopy, which is one of the fastest growing fields in microscopy. Imaging in the visible and infrared bands. The infrared band is used in conjunction with visual imaging. It is also used in visual processing and remote sensing. Imaging in microwave band. Radar is the application of microwave imaging. Its unique ability is to collect data over virtually any region at any time without regarding the weather or ambient light conditions. Imaging in radio band. Radio band imaging is used in medical and astronomy fields. In medicine, radio waves are used in MRI, magnetic resonance imaging. It places a patient in a powerful magnetic field and passes radio waves through the body in short pulses. Ultrasound images. Used to determine development of health. Ultrasound waves are generated using the following procedure. Ultrasound system transmits a high-frequency sound pulse into the body, usually at 1 to 5 MHz. The sound wave travels through the body and hits the boundary between tissues. Some of the waves are reflected back to the probe and relayed to the computer. The machine calculates the distance between the probe and boundaries by using the speed of sound and time required for each echo to return. The system displays the intensities and distance of the image displays on a screen, forming a two-dimensional image. Transmission electron microscopy. Transmission electron microscopy, TEM, is a microscopy technique in which a beam of electrons is transmitted through an ultra-thin specimen, interacting with the specimen as it passes through. The image is formed from electrons passing through the specimen. The image is magnified and focused onto an imaging device, such as a fluorescent screen on a layer of photographic film. TEMs are capable of imaging at a significantly higher resolution than light microscopes. TEMs are used in many applications like cancer research, virology, material science, as well as in pollution control, nanotechnology, and semiconductor research. A TEM image of poliovirus is shown on the screen. A poliovirus is 30 nm in size. Scanning electron microscope. Electron microscope that produces images of a sample by scanning it with a focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that can be detected about sample surface topography and composition. SEM can achieve resolutions better than 1 nanometer. Specimens can be observed in high vacuum, low vacuum, and wet conditions, and at a wide range of cryogenic conditions. These pollen grains taken on an SEM show the characteristic depth of field of SEM micrographs. Some basic relationship between pixels. In this section, we can learn a lot of things about relationship between digital image and pixels. 1. Neighbors of a pixel. A pixel has 4 neighbors in east, west, north, south directions. Pixel can be represented as P. A pixel P has 8 neighbors if the neighbors are in 8 directions, such as east, west, north, south, northeast, northwest, southeast, southwest. A pixel P coordinates x, y has 4 horizontal and vertical neighbors whose coordinates are given by x plus 1, y, x minus 1, y, y plus 1, x, y minus 1, x. The 4 diagonal neighbors of P have coordinates x plus 1, y plus 1, x plus 1, y minus 1 into x minus 1, y plus 1, x minus 1, y minus 1. Neighbors of a pixel are denoted by NDP. 4 neighbors of a pixel are denoted by N4P and 8 neighbors of a pixel by N8P. 2. Adjacency, connectivity, regions and boundaries. Adjacency. A set of intensity values are used to assign adjacency. V is used to denote intensity values. In binary image, if V equals 1, the adjacency value of pixel is also 1. In grayscale image, the idea is same as binary image, but V has more elements. In adjacency, pixel intensity values range from 0 to 255. Set V could be subset of these 256 values. 3. Types of adjacency. For adjacency, 2 pixels of P and Q with values from V are 4 adjacent if Q is in set N4P. 8 adjacency. 2 pixels of P and Q with values from V are 8 adjacent if Q is in set N8P. M adjacency. Mixed adjacency. Pixels of P and Q with values from V are M adjacent if Q is in N4P, Q is in NDP and set N4P. Intersection N4Q has no pixels whose values from V. Mixed adjacency is modification of 8 adjacency. It is used to eliminate ambiguities that often rise when 8 adjacency is used. Connectivity. S represents subset of pixels in an image. 2 pixels P and Q are connected in S. That set of pixels which are connected to it in S is called connected component of S. If it has only one component, then set S is called connected set. Regions and boundaries. A boundary is also called as border or contour. Boundary of the region R is a set of points that are adjacent to the points in the complement of R. In other words, boundary of a region is a set of pixels in the region that have at least one background neighbor. Inner border background is distinguished from outer border background. If region R is to be an entire image, then boundary is defined as a set of pixels in the first and last row and column of the image. The boundary of a finite region forms a closed path. Distance measures. For pixels P, Q, Z with coordinates x, y, s, t, v, w, d is a distance function or metric if d of P, Q is greater or equal to 0, d of P, Q equals 0 if P equals Q, d of P, Q equals d of Q, P, d of P, Z equals d of P, Q plus d of Q, Z. Euclidean distance between P, Q is classified as dE of P, Q equals x minus s squared plus y minus t squared. For this distance measure, the pixel having a distance less than or equal to some value r from x, y are the points contained in a disk of radius r centered at x, y. d4 distance between P and Q is defined as d4 of P, Q equals mod of x minus x plus mod of y minus t. In some cases, the pixel having a distance less or equal to some value r form a diamond centered at x, y. For example, d4 distance less than or equal to 2 from x, y following contour constant distance. The pixels with d4 equals 1 are the neighbors of x, y. d8 distance between P and Q is defined as d8 of P, Q equals max of mod of x minus s minus mod of y minus t. In some cases, the pixel having a distance less or equal to some value r form a diamond center at x, y. d8 distance is less than or equal to 2 from x, y following contour constant distance. Fundamentals of digital image. Visual perception. In presenting the output of an imaging system to a human observer, it is essential to consider how a viewer transforms it to information. Visual perception is important to image fidelity, which aids in field of image processing algorithm and image systems. Visual image data itself represents spatial frequencies of an object. The perceived information may be represented by attributes such as color, brightness, etc. Structure of the human eye. 3 membranes enclose the eye. These are the cornea, sclera and choroid, retina. At its anterior extreme, the choroid is divided into the ciliary body and the iris. The latter contracts or expands to control the amount of light that enters the eye. Elements of visual perception. When the eye is properly focused, light from an object outside the eye is imaged on the retina. 2 kinds of light receptors distribute on the retina, cones and rods. Cones are primarily located in the central portion of the retina, called the fovea, and are sensitive to color. They function best in relatively bright light, so cone vision is called bright light vision. Rods are distributed over the retinal surface. Rods serve to give a general, overall picture of the field of view. They are not involved in color vision and are sensitive to low levels of illumination. Rod vision is called dim light vision. Around the region of the emergence of the optic nerve, there are no receptors, and this results in a so-called blind spot. Humans usually have 3 kinds of cones with different photopsins, which have different spectral response curves, resulting in trichromatic vision. Interestingly, some people have 4 or more types of cones, giving them tetrachromatic vision. 3 types of color-sensitive cones are there in the retina of the human eye, corresponding roughly to red, green, and blue sensitive detectors. Wavelength responsiveness of rods compared to that of 3 types of cones. The dashed gray curve is for rods. Image formation in the eye. Muscles within the eye can be used to change the shape of the lens, allowing us to focus on objects that are near or far away. An image is focused onto the retina, causing rods and cones to become excited, which ultimately send signals to the brain. Perceived brightness is not a simple function of intensity. Visual system tends to undershoot or overshoot around the boundary of regions of different intensities called as Mach bands. A region's perceived brightness does not only depend simply on its intensity, but on its surrounding regions. Such a phenomenon is called simultaneous contrast. Optical illusions. Our visual systems play lots of interesting tricks on us. It is still not fully understood yet. Light and the electromagnetic spectrum. Light is just a particular part of the electromagnetic spectrum that can be sensed by the human eye. The electromagnetic spectrum is split up according to the wavelengths of different forms of energy. Wavelength lambda equals C by F. Photon energy E equals hc by lambda, so E equals hf, where c is the speed of light and h the Planck's constant. The colors that we perceive are determined by the nature of the light reflected from an object. In addition to frequency, three basic quantities are used to describe the quality of a chromatic light source. Monochromatic light, light that is void of color. Chromatic light, light that spans the electromagnetic energy spectrum from 0.43 to 0.79 micrometers. Radiance, the total amount of energy that flows from the light source, measured in watts. Luminance gives a measure of the amount of energy an observer perceives, measured in lumens. Brightness, it is a subjective descriptor of light perception that is practically impossible to measure. Fundamental steps in digital processing. Please view the diagram. Image acquisition. Image acquisition is very simple. Images are already in digital form. It involves pre-processing, which is called scaling. Image enhancement. Image enhancement technique is used to improve quality of an image. It is familiarly used in digital image processing. It is a very simple technique. Subjective area of image processing. Image restoration. It is used to improve appearance of an image. This is the objective area of image processing. This is based on mathematical or probabilistic model of image degradation. Color image processing. Extracting features of interest in an image. This is an area that has been gaining in importance because of significantly increased use of digital image over Internet. Compression. Compression is used to reduce storage required to save an image, bandwidth required to transmit it. Morphological processing. It deals with tools for extracting the imaging components that are used in representation and description of shape. Segmentation. Segmentation is defined as partition of images into its constituent parts or objectives. This is a difficult task in image processing. It gives accurate results. This represents a successful solution for imaging problems. An erratic segmentation algorithm almost always guarantees eventual failure. The more accurate the segmentation, the more likelihood of success. Representation and description. Representation. Representation, which follows the segmentation stage, is usually raw pixel data constituting either boundary or region. Boundary representation. This is appropriate when focus is on external characteristics such as corners and inflections. Region representation. This is appropriate when focus is on internal characteristics such as textures and skeletal shape. Representation is transforming of raw data into forms suitable for subsequent computer processing. Description. It is defined as specialized for describing data so that features are highlighted. It is used to extract features of attributes that result in some quantitative information. It is also called as feature collection. It is a process that aligns a label to an object based on its descriptors. Components of image processing system. Please view the diagram. Image sensor. With reference to sensing, two elements are required to acquire digital images. These are sensor, digitizer. Sensor, a sensor that is sensitive to energy radiated by the object. Digitizer, is a device for converting output of physical sensing device to digital forms. Specialized image processing hardware. It has a digitizer and hardware which perform primitive operations such as arithmetic logic unit. ALU performs arithmetic and logical operations for entire images. ALU is used for reduction of noise in images. This hardware is also called as front-end subsystem. Computer. It can range from PC to supercomputer, used to achieve a required level of performance. Software. It has specialized modules to perform specific tasks. Mass storage. Storage capability is important in digital imaging processing. It consists of three types of storages. These are short-term storage, online storage, archival storage. Short-term storage is used during processing. Online storage is used for relatively fast recall, and archival storage is characterized by infrequent access. Image display. It displays images. Hard copy devices used for recording images includes laser printers, film cameras, heat-sensitive devices, inkjet units, digital units such as optical and CD-ROM disks. Image sensing and acquisition. Sensor arrangements are used to transform illumination energy into digital images. Image creation is based on two factors: illumination source, reflection or absorption. Illumination source or reflection of energy from that source by the elements of the scene being image. Image acquisition. Digital image acquisition is the creation of digital images such as of a physical scene or of the interior structure of an object. The term is often assumed to imply or include the processing, compression, storage, printing, and display of such images. Image sensing. Image sensors used to convert optical image to electrical signals. It is used in imaging systems and digital cameras. Image acquisition using a single sensor. The most common sensor of this type is the photodiode, which is constructed of silicon materials and whose output voltage waveform is proportional to light. The use of a filter in front of a sensor improves selectivity. This is one of the ways to obtain high-resolution images. Other similar mechanical arrangements use a flatbed, with the sensor moving on two different linear directions. These types of mechanical digitizers are sometimes referred to as micro-densitometers. Image acquisition using sensor strips. A geometry that is used much more frequently than single sensors consists of an inline arrangement of sensors in the form of a sensor strip. The strip provides imaging elements in one direction. Motion perpendicular to the strip provides imaging in the other direction. This is the type of arrangement used in most flatbed scanners. Sensing devices with 4,000 or more inline sensors are possible. Inline sensors are used routinely in airborne imaging applications, in which the imaging system is mounted on an aircraft that flies at a constant altitude and speed over the geographical area to be imaged. One-dimensional imaging sensor strips that respond to various bands of the electromagnetic spectrum are mounted perpendicular to the direction of flight. The imaging strip gives one line of an image at a time, and the motion of the strip completes the other dimension of a two-dimensional image. Lenses or other focusing schemes are used to project the area to be scanned onto the sensors. Sensor strips mounted in a ring configuration are used in medical and industrial imaging to obtain cross-sectional or slice images of 3D objects. A rotating X-ray source provides illumination, and the portion of the sensors opposite the source collects the X-ray energy that passes through the object. The sensors obviously have to be sensitive to X-ray energy. This is the basis for medical and industrial computerized axial tomography (CAT) imaging. It is important to note that the output of the sensors must be processed by reconstruction algorithms whose objective is to transform the sensed data into meaningful cross-sectional images. Image acquisition using sensor arrays. Individual sensors can be arranged in the form of a 2D array. Numerous electromagnetic and some ultrasonic sensing devices are arranged frequently in an array format. This is also the predominant arrangement found in digital cameras. A typical sensor for these cameras is a CCD array, which can be manufactured with a broad range of sensing properties and can be packaged in rugged arrays of 4,000*4,000 elements or more. CCD sensors are used widely in digital cameras and other light sensing instruments. The response of each sensor is proportional to the integral of the light energy projected onto the surface of the sensor, a property that is used in astronomical and other applications requiring low noise images. The first function performed by the imaging system is to collect the incoming energy and focus it onto an image plane. If the illumination is light, the front end of the imaging system is a lens which projects the viewed scene onto the lens focal plane. The sensor array, which is coincident with the focal plane, produces outputs proportional to the integral of the light received at each sensor. Digital and analog circuitry sweeps these outputs and converts them to a video signal, which is then digitized by another section of the imaging system. The output is a digital image. Imaging sampling and quantization. To create a digital image, we have to convert continuous sense data to digital form. It involves two processes. These are sampling, quantization. To convert to digital form, we have to sample the function in both coordinates and its amplitude. Sampling. Digitizing coordinate values are called as sampling. Quantization. Digitizing the amplitude values are called quantization. Number of intensity levels typically is an integer power of 2. Often 256:1 byte equals 8 bits per pixel. The discrete levels are equally spaced. Sampling. Effects of reducing spatial resolution. Sampling of function f of x, y, fe of x, y equals f of x, y into sigma I, sigma j, del of x minus I, delta x, y minus j delta y, delta x. Sampling distance in direction of x delta y, sampling distance in direction of y. The value of function x, y at x equals I delta x and y equals j delta y. The mean value of function x of y around I delta x, j delta y. If function x, y is weighted by h and integrated over r, f bar of I delta x, I delta y equals integrated over f of x, y into h of I delta x minus x, j delta y minus y into dx dy. Sampling distance limits lead to a reduction in resolution. Structures of about the scale of the sampling distance and finer will be lost. Sampling theorem. We will obtain a periodic structure correctly only if we take at least 2 samples per wavelength. Else, Moore effect. Sampling theorem is a fundamental bridge between continuous time signals, often called analog images, and discrete time signals, often called digital images. Representation of images. A rectangular grid is only the simplest geometry for a digital image. Delta x equals delta y. Other geometrical arrangements of pixels and geometric forms or elementary cells are possible. Digitization process requires decision about values for m, n and for L, discrete grade levels allowed for pixels. Number of grade levels typically is an integer power of 2. L equals 2 raised to the power of k. Discrete levels are equally spaced and that they are integers in interval 0 to L minus 1. This is known as dynamic range of image. Number of digitized bits b required to be stored in an image. B equals m star n star k. If m equals n, equation becomes b equals n squared k. Spatial and intensity resolution. Spatial resolution. Sampling is the principal factor of determining the spatial resolution of an image. It measures the smallest discernible detail in an image. Spatial resolution can be starred in a number of ways, such as line pairs with unit distance and dots per unit distance. Intensity resolution. It is referred as the smallest discernible change in intensity level. Intensity levels usually is an integer power of 2. Number of bits used to quantize intensity is called as intensity resolution. Image interpolation. It is a basic tool used extensively in tasks such as zooming, shrinking, rotating, and geometric corrections. Interpolation is a process of using known data to estimate the values at unknown locations. Nearest neighbor interpolation. It assigns each new location the intensity of its nearest neighbor in the original image. Bilinear interpolation. Using 4 nearest neighbors to estimate intensity values at given location. Let x, y be the coordinates location to which we assign intensity value, and v of x, y is intensity value. Thus, equation of bilinear interpolation the assigned value using following equations. V of x, y equals ax plus by plus cxy plus d. Bicubic interpolation, which involves 16 nearest neighbors of the point. Intensity value assigned to point x, y is obtained using equation v of x, y equals summation of I equals 0 to 3, summation of j equals 0 to 3, aij, x raised to the power I, y raised to the power of j. Stereovision. Stereopsis, from the Greek stereo meaning solid and opsis meaning appearance or sight, is a term that is most often used to refer to the perception of depth and three-dimensional structure obtained on the basis of visual information deriving from two eyes by individuals with normally developed binocular vision. Goal of stereovision. The recovery of 3D structure of a scene using 2 or more images of the 3D scene, each acquired from a different viewpoint in space. The images can be obtained using multiple cameras or one moving camera. The term binocular vision is used when 2 cameras are employed. Example of stereo imaging. Using 2 or more spatially separated cameras to form images from different directions, from left and right direction. The depth information is then extracted from the differences. Images A and B are left and right images from a stereoscopic image pair. Here we have shown image C, composite image of stereo vision. Stereo setup and terminology. Fixation point, the point of intersection of the optical axes. Baseline, the distance between the centers of projection. Epipolar plane, the plane passing through the centers of projection and the point in the scene. Epipolar line, the intersection of the epipolar plane with the image plane. Conjugate pair, any point in the scene that is visible in both cameras will be projected to a pair of image points in the 2 images. Disparity, the distance between corresponding points when the 2 images are superimposed. Disparity map, the disparities of all points form the disparity map, can be displayed as an image. Triangulation, the principle underlying stereovision. The 3D location of any visible object point in space is restricted to the straight line that passes through the center of projection and the projection of the object point. Binocular stereovision determines the position of a point in space by finding the intersection of the 2 lines passing through the center of projection and the projection of the point in each image. 2 problems of stereo. 1. The correspondence problem. 2. The reconstruction problem. The correspondence problem. Finding pairs of matched points such that each point in the pair is the projection of the same 3D point. Triangulation depends crucially on the solution of the correspondence problem. Ambiguous correspondence between points in the 2 images may lead to several different consistent interpretations of the scene. Reconstruction problem. Given the corresponding points, we can compute the disparity map. The disparity map can be converted to a 3D map of the scene, that is, recover the 3D structure if the stereogeometry is known. Recovering depth reconstruction. Consider recovering the position of P from its projections PL and PR. XL equals f of x1 by z1, or XL equals x1 z1 by f, and XR equals f of xr by zr, or XR equals xr zr by f. In general, the two cameras are related by the following transformation. PR equals R into PL minus T. Using ZR equals ZL equals Z and XR equals XL minus T, we have XLZ by F minus T equals XRZ by F, or Z equals TF by D, where D equals XL minus XR is a disparity, that is, the difference in the position between the corresponding points in the two images. Stereo camera parameters, intrinsic parameters, characterize the transformation from image plane coordinates to pixel coordinates in each camera. Extrinsic parameters, R, T, describe the relative position and orientation of the two cameras. PR equals R into PL minus T, aligns right camera with left camera. Can be determined from the extrinsic parameters of each camera. R equals RR, RL raised to the power of T. T equals TL minus R raised to the power of T into TR. Kinect cameras. Software is developed by a company named RARE. Camera technology is developed by an Israeli. Similar to stereo cameras, Kinect cameras are also used to calculate depth. Able to create a depth map of an image, it uses an infrared camera for this purpose and does not use the dual camera technique. Next generation of motion control. A depth image is computed by calculating the distortion of a known infrared light, IR pattern, which is projected into the scene. IR Kinect is used to improve depth images by combining structured light with IR stereo. Kinect offers the potential to transform how people interact with computers and windows. Enables user to control and interact with the application. 3D scanner system is called as light coding. Fast and accurate optical sensor, which is used to extract animation. Embedded devices in multiple industries. Education, healthcare, transportation, game. Kinect system consists of an infrared projector, a color camera, an infrared sensor. Multi-array microphone that enables acoustic source localization, ambient noise suppression. The depth sensor captures video data in 3D under any ambient light condition. Infrared laser projector, monochrome CMOS sensor. The Kinect software is capable of automatic calibration based on gameplay, based on physical environment, accommodating for the presence of furniture or other obstacles. Kinect is capable of tracking up to 6 people, performing motion analysis for 2 active players, feature extraction of 20 joints per player. Kinect features full-body 3D motion capture, gesture recognition, facial recognition, voice recognition capabilities. Stereo and Kinect cameras. Kinect is used to create depth of an image and is also used in infrared camera, but not used in dual camera techniques. Kinect camera is used in robot, and stereo is also used in robot applications, such as robot remote sensing and controlling. Applications of Kinect: IP lab, virtual dressing room, interactive training, merges real and virtual worlds, Kinect in hospitals, Kinect quadrocopter, depth, the flying machine, virtual piano. Conclusion. In this chapter, we have covered the following in detail: fundamentals, purpose, application, image processing system, components, image sensing and acquisition, sampling and quantization, neighbors of a pixel, adjacency, connectivity, regions and boundaries, distance measures, stereo vision.